Hello everyone and welcome back to MV Tutors. I'm Tsolo and I'm going to continue with the application of electrolysis. I spoke last time mentioning them, so we're going to go through each one of them. Okay, so they normally ask these questions on the electrochemistry, either question 8 or question 9. So let's see what is actually happening. First, we're going to start with electroplating. Okay, I did make an example of silver, electroplating cutlery with silver. Okay, so I'll start with that. So what happens here? Okay, like we said, the anode is connected to the positive terminal of the battery. Okay, and as a result, because oxidation occurs at the anode, electrons are being lost. Okay, so therefore you'll have a positive charge, but we don't really have a positive charge because the electrons are leaving. We have a positive charge because it's connected to the positive terminal of the battery. Okay, so at the anode, we actually have the pure silver. Okay, so whatever you place at the anode, it is what you want to coat. Okay, what do you want to coat? Do you want to coat silver or gold or whatever onto whatever object, either a ring or a spoon, or I don't know, have you ever seen like toys for kids like swords and cars and you want to electroplate them? That's basically what you use electroplating for. So here I'm going to go with silver in this example. We actually have the anode is actually the silver, okay? Solid silver. All right, so what happens? So during this electrochemical process, okay, where electrical energy is converted to or produces chemical energy, all right, we have that power source over there. Once it starts up in your solution, in your electrolyte, okay, because now the electrons are leaving this solid silver, you are now going to start forming silver ions in this solution, okay, in this electrolyte. All right, and then as the electrons are going over to the cathode, where reduction occurs, okay, so basically at the cathode you have all these silver ions, okay, and then they start reducing from ions to the solid. So around your, I use the fork here. So around your fork, you will then start having the silver, surrounding the fork or plating the fork. Okay? So yeah, that's basically, so the fork, let's talk about the fork. So you have a metal there that is of less quality, or is the least expensive, okay, because silver is quite expensive. And I did mention in the first video of electrochemistry, that the electrolysis or the electrolytic cells, that process is very expensive because we're taking electrical energy and we're converting it to chemical. All right, so as you're electroplating here, okay, as these silver ions take up the electrons, you're going to end up with a solid silver. Okay, these are in aqueous solution. All right, these ions start, because they're positively charged, they will go to the negatively charged electrode, okay, which is the cathode. So these silver ions go and attach themselves there at the fork, and you start seeing a thick layer, or not even thick, whatever thickness they want, but you start seeing a layer form around the very thing that you want to electroplate. Okay, so yeah, in summary, basically on your anode side you have the solid, okay, and what is the solid doing? Well, because of oxidation, okay, the loss of electrons, you start forming silver ions, okay, because you're losing these electrons. And then on the other side, at the cathode, you are gaining electrons, okay, and then the solid starts forming. So basically electroplating, I like examples or other questions because you know what happens. Oxidation, you have your, if you were to do your redox, okay, on the oxidation side, oxidation, where oxidation occurs, you have this, okay, where your solid ends up into ions, okay, because it has lost electrons. And then on the reduction side, okay, you have those ions there that are coming to the cathode, okay, they take up electrons, and then you have your silver solid, okay, that is busy electroplating your cutlery or whatever it is that you want to electroplate. Okay, so I think, yeah, that's pretty much it that I wanted to cover. So we'll go to the next one, which is the purification of copper. The one thing I forgot to mention with regard to the type of metal you would use to electroplate another one. Okay, it's not only metals that are electroplated, even plastics are. But like silver for one, you would want to coat another metal with, first of all, an attractive metal. Silver is. It's quite expensive, so you put a thin layer, not a thick one. But another thing is you want to use a metal that is not corrosive. Because imagine they are having your cutlery and now all of them corrode. So you want a metal that is long lasting, that doesn't corrode. Okay, so if you're going to look into the type of metals that you're going to use for electroplating, use ones that do not corrode. Okay, then we come to the purification of copper. I chose copper, it's the most used example. You could do purification for something else like gold or whatever metal that you're taking from the earth, through mining processes. So in this case, with copper, thing is you start by having your impure copper. Okay, sometimes this what is it? This electrolytic cell can be, you can have one thing, you don't have to put all those things. Like they have your impure copper and they have your pure copper. Okay, so you can have something like that. Okay, I just drew what would probably happen in industry. Okay, so you have your impure copper, the one that I drew here. Okay, the one that is connected to the positive terminal of the battery, which is the cathode. Okay, and then you have your pure copper, okay, which is connected to the cathode. The whole thing with this is you want the copper, the pure one, that is found embedded in the impure copper to really just come out, okay, and go and attach itself to the pure copper. And you do that, it's achieved actually through electrolysis. Okay, so that is for the purification of copper. So when you find that impure copper as you are mining, it will come with other metals in it, maybe for example like gold, silver, platinum, whatever. So you'd find that as this whole electrolysis process is going on, the impurities, which are the other metals, maybe let me put them in this color, orange. Okay, make it a bit thicker. So they come here to the floor, okay, because they are not going to be oxidized or reduced or anything like that. Okay, and how do I know that they won't be oxidized and reduced? Well, basically, the table of standard reduction will actually, standard reduction potentials will actually tell us if your silver and your gold and your platinum or whatever is actually strong enough to form part of the confidence that we have here by looking at the standard reduction potential is that your impurities will not be reduced. Okay? Ooh, what is my pen doing? Okay. So yeah. So those impurities will not be reduced. They will not form part of this pure copper that we're trying to get out. Okay, so they will come here and they will settle at the bottom, okay, and they will be taken and purified by themselves. Okay, so that's what happens to the impurities. And another thing is, as your copper is busy forming your pure copper, don't forget that at the anode, where oxidation occurs, the mass will start reducing. Okay, it will start reducing on the side and will become smaller and smaller. Okay, but on the cathode side, it will actually start increasing. So you'll have, a bigger coating basically. Okay, and let's see what kind of reactions are we expecting at the cathode and what reactions are we expecting at the anode. Okay, my pen is a little bit malfunctioning. I don't know what's happening there. But yeah, so you start off at the anode with your pure copper. Okay, let's reduce the size. Okay, sorry, impure copper at the anode. Okay, but the pure part of it. Okay, so it's all solid. It's quite similar to the electroplating. Okay, and oh, by the way, the electrolyte that is used here is your copper sulfate. But you don't have to worry about the sulfate. It won't reduce or oxidize. Well, actually, it's a negative. It has a negative charge, so it won't oxidize. Okay, so you can be fine with using copper sulfate as your electrolyte. So now you have your copper solid at the anode, okay, and then it starts forming copper 2 plus ions, okay, and because we have a charge of 2 plus, okay, every time oxidation occurs, you're going to lose 2 electrons. Okay, so your electrons are pretty much gonna go out there. Okay, and then at the cathode, where reduction occurs, your electrons are gonna come through. Okay, and remember, you're gonna start off by having your copper 2 plus ions, and you're gonna take in the electrons, and then what you're forming at the end is your copper solid. So basically that is what happens. You start losing weight, or rather losing mass there at the impure copper, because the actual copper ions that form during oxidation, that you'll have in your solution, you also have the sulfates somewhere there. Okay, and then at the cathode, like I said, you will have an increase in mass for all of them. Okay, and you'll see that now it starts purifying. Okay, and at the end, whatever is impure will end up settling at the bottom there of your whatever you're using, and you're going to take those impurities and go and purify them by themselves. So that is basically the purification of copper as well. And then what are we going to look at? Oh, even here, what I forgot to show is, as the silver is forming ions at the anode, remember it is also losing mass. Okay, the mass is actually reducing because it'll come and form the side to electroplate whatever it is that you want, in this case the fork. Okay, so that is the purification of copper. Okay, so thirdly, we're going to look at the chlor-alkali industry. Okay, and here we're basically going to use electrolysis for us to end up getting chlorine gas, hydrogen gas, and sodium hydroxide. Okay, and basically those products, they are used, in everyday products, like sodium hydroxide. You normally use that for your soaps. That's the only thing I can think of. Your chlorine, you use it to clean your pools, the water basically for water purification, as well as bleaches. And hydrogen, well, you're going to use that for margarine, and other things as well. Okay, there are many other uses. You can actually go through your notes in detail to find that out. But also, as much as we are getting these products, they also have side effects. Okay, like chlorine gas is actually quite harmful to inhale. Okay, hydrogen gas, we know that it contributes to the global warming, depletion of the ozone layer. And then you have sodium hydroxide as well. It can be poisonous, I think. I believe it can be corrosive. Okay, so yeah, that's actually the downside of it. But I mean, we need these products, right? So that's why we have this in industry. So what actually happens? Basically, you are going to take your saturated sodium chloride, okay? Oh, and one thing, you know how with an electrolytic cell, you always have your electrodes in one solution. Here, well, they kind of are, but then we have in between here, I don't know if you noticed, we have in between here a semi-permeable membrane, okay? So we have a membrane over here, okay? You can see it there. And basically, there are actually different membranes that you could use. You know, there's one that's actually called the mercury cell. Okay, if you go and actually read this, there should be a section in your textbook, the chloralkali industry, and you'll see that with this permeable membrane, this membrane actually it works the best. You know, it uses less energy, it is less expensive than the others, and the products that you get are in the purest form that you could get. So the membrane cell actually wins. So you have your mercury cell that you could use. There's also a diaphragm cell. And apparently in industry, the diaphragm is preferred. I don't know, maybe it's because it has been an older method that has been used, but this semi-permeable membrane is quite recent. So only, I won't say now as in like 2021, but until recently it has been adapted. And the other two methods, not used anymore. So basically, you have your sodium chloride that is saturated, right? It enters in here, and you have water as well on the right hand side here that also enters. So you have water and you have sodium chloride. So in your anode compartment, remember on the positive side, the electrode connected to the positive terminal is the anode, the one connected to the negative terminal is the cathode. So for your anode compartment, you have in here your sodium ions, okay, as well as your chlorine ions. Okay, my pen is misbehaving, guys. I don't know why. Yeah, quite a disappointment. But if we're looking at the whole equation, basically you have sodium chloride, okay, and then with water and the products that we're expecting, like I said, you're gonna have hydrogen, chlorine, as well as sodium hydroxide, which is also known as caustic soda. Okay, so you're gonna have your sodium ions on the anode compartment as well as your chlorine ions. Okay, yeah, your chlorine ions. Okay, let's hope the pen works properly. Yes, or chloride ions. Okay, so you have chloride ions, sodium, sodium. And basically, what would then be the purpose of this membrane? Well, the membrane actually allows the sodium to go through, okay? Because they say it's permeable, it means it can allow stuff to go through, but only sodium goes through, okay? While chlorine or the chloride ions are actually left behind in the anode compartment. So, and it makes sense, guys. Remember now your electrode is positively charged for the electrolytic cell. And because it's positively charged, your positive ion will repel it. So it will go over to the other side. It actually passes through the membrane. And what is remaining? Your negatively charged ion, which is your chloride ions. And your chloride ions then attach themselves to the anode, okay? And they become oxidized. When they become oxidized, they lose electrons, remember? And as they lose electrons, okay, they you're gonna have chlorine, or rather chloride. It is oxidized, it loses an electron each, and then you're just gonna have Cl by itself. But hopefully, because of the octet rule, you can't have chlorine going by itself. It comes in pairs, okay? So you have two chlorine atoms, and they're coming out here, bubbling out because they are now gases, okay? And therefore you have one of the products, which is chlorine gas. Okay, on the other side, you have H2O, water. right? So it means you have your hydrogen ions, okay? They have your hydrogen ions, and you also have your hydroxide ions, as it's, it's there. And what will happen is your positively charged ion, which is the hydrogen, or yeah, the hydrogen ion, it'll be attached, or rather attracted to your cathode, because your cathode is negatively charged. And as it does that, it is gaining an electron. Remember, the electrons coming through, given off by the chlorine or the chloride ions. Okay, and then once that happens, you have your positively charged ion, it accepts an electron, and then it becomes H. Okay, and also when we have hydrogen, hydrogen only has one electron in its orbital. Okay, so it needs another hydrogen to attach to it, right? So it doesn't go off alone. It is the only, or one of, those that do not fulfill the octet rule. Hydrogen is an exception, and there's a whole theory behind it. But yes, so now you start having these bubbles of hydrogen gas, okay, and therefore you have your second product coming out. Okay, so now remember your sodium, it passed through the membrane and it went over to the cathode compartment. Okay, so now you have a positively charged ion, which is sodium. I guess you would ask yourself, since sodium came in here, okay, wasn't it competing with hydrogen to see if it will be reduced? What's happening. That's where we consult with our table of standard reduction to see which one is likely to be reduced. Is it hydrogen or is it sodium? And remember our rules. Okay, our rule says that sodium, it is in group 1, it is an alkali or alkali metal. Okay, so we have a look between the alkali metals and the hydrogen. The one, if your alkali metal has a negative voltage to it, then the hydrogen will be reduced. If the sodium, in this case, the alkali metal, or any metal for that matter, if it has a negative voltage, if it has a positive voltage, then it will be reduced. So let's have a look at our table of standard reduction potentials. Where is hydrogen and where is the sodium? Okay, so we know hydrogen has a voltage of 0 volts, right? Potential difference of 0 volts. So now let's go look for sodium. Okay, so I see sodium over here. Okay, you can see it. I don't know if you can see my cursor, but yes, there is sodium, and it has a negative charge, guys. It has a negative 2,71. So definitely, if we're comparing sodium and hydrogen, we know that hydrogen wins. Okay, it takes a spot. All right, so yes, hydrogen in this case will be reduced to hydrogen gas. Now the sodium is there, frolicking in the cathode compartment, like, okay, what am I meant to be doing now? And then the hydroxide is like, hey, yo, you want to hook up? And yay, they can hook up. And then you have the last product, which is sodium hydroxide, also known as caustic soda. Caustic, caustic. I don't know if I'm pronouncing it right. But yes, it's caustic soda or sodium hydroxide, okay? And like we said, there are uses for it. So you have your three main products, your chlorine gas, hydrogen gas, as well as caustic soda or sodium hydroxide. And then on this side here, well, let's say there are this depleted sodium chloride. Well, basically, the sodium that didn't get through the membrane and the chlorine ions or the chloride ions that did not oxidize, well, yeah, they just came out, I guess. So that is basically the chloralkali industry. But what actually happens there at the anode? Okay, we know that oxidation happens at the anode. So what did you have? You had your chlorine, okay? Let's actually go look for it in the table of standard reduction. You have your chlorine being oxidized, right? Losing its electrons and it forming chlorine gas. And then there at the cathode where reduction occurred, well, we had hydrogen being reduced to hydrogen gas. So we're going to go look for those at the table of standard reduction potential. Okay, so chlorine, let us see, where is chlorine? Okay, so I see iodine, I see bromine, chlorine must be somewhere here. So firstly, we started, so how do we write it on the anode side? When you get to the anode, guys, the way the tables are presented to us, they are presented in such a manner that the way it's written, you can write it exactly as it is for the cathode, but for the anode, it's actually different. You have to swap it around. So we started with chlorine or chloride ions, right? And you can see that is on the right hand side, so we're going to have to swap it around. So we're going to have chlorine gas and 2 electrons that it released. Okay, so at what was oxidized? Well, we had our chloride ion, okay, and it gave away some electrons, let's say gave away 1 electron each, but what was the product? The product was chlorine gas. And because we have chlorine and it has to fulfill the octet rule, it can't go by itself, we have 2 chlorine atoms. So now we need 2 chloride ions, and as a result of that, we're going to need 2 electrons. Okay, so I hope you see how it's balanced, but it's written out for us, so you can just copy it from the table. Yeah, so that pretty much is what happens at the anode compartment. Okay, this is the half reaction that you are going to write down. But what happens at the cathode compartment? Okay, guys, so we had hydrogen atoms, hydrogen ions that were reduced to hydrogen gas. So let's go see where we can find hydrogen gas. Okay. So start from the beginning. Okay, so I see here we have water, okay, with 2 electrons that produce hydrogen and hydroxide. But remember, we have that standard where the potential difference is 0. We have hydrogen ions there that took in, because of reduction, it added or it gained electrons and formed hydrogen gas. So which of the two do we honestly take? This one with just hydrogen or the one with water? Okay, in this case, we're going to take the one with water because remember you put water in, right? And from that water, you got your hydrogen as well as your hydroxide. Okay, so I know the natural tendency is to go with this one where you have your hydrogen ions because that's what we see, right? But it's actually water. Okay, so added or rather gained 2 electrons, and then we got hydrogen as well as hydroxide ions. Okay, so let us do that one. Okay, so you had water, and remember, because on the cathode side we write the half reaction as we find it on the table. Okay, don't try anything else. So we have water, okay, and we had that electron, and the products that we had was hydrogen gas, okay, as well as hydroxide ions. Okay, so that's aqueous solution, that's actually a liquid. So now what do? We need to balance the equation. So we see we have 3 hydrogens on the right hand side and we only have 2. So we are going to put a 2 here because now we have 4, and that's why we're going to put a 2 there. And because now we need to balance everything, even the electron has to get a 2. Okay, so basically that is the half reaction at the cathode. And one thing I forgot to mention with the membrane, what it does allow, it allows positive ions through. That is why the sodium could go through. Okay, and you do have in small quantities, like very small quantities, you do have also water going through this permeable membrane, but it does not allow the anions to go through. That's why chlorine won't pass to the cathode compartment, and that is why the hydroxide also will not pass through to get to the anode compartment. Okay, so I hope that is clear. And then we are going to look at the extraction of aluminium from bauxite. Okay, so basically what happens here, you have bauxite, which is like, again, an impure substance which has in it aluminium. Okay, so you take your bauxite, okay, and then from it, when you purify it, what you would get is aluminium 2 oxide. Okay, the reason why aluminium has 2 at the bottom and oxygen has 3, remember aluminium has a charge of 3 plus and oxygen has a charge of 2 minus. So if you do cross multiplication, aluminium gets 2 and oxygen gets 3. Okay, so you have this impure, you have bauxite basically, and from it, through purification, you can get aluminium oxide. But here's the thing with aluminium oxide, guys. For you to break it apart, né? Remember, this is a solid. This bauxite here, it's like solid. Okay, and through electrolysis, you want to get the ions separate. You want to get it in solution. Okay, so aluminium oxide, it has quite a high boiling point. If you want to get it to be molten all by itself from that solid, you would need to boil more than 2000 degrees Celsius. And that in itself is very costly. This extraction of aluminium is very, very, very costly. Actually, we find a lot of aluminium, I don't know in terms of the whole world, but South Africa does import bauxite, okay, and it imports it, and whoever's buying it will purify it, because the purification process of it, or extracting aluminium from bauxite, is a very expensive process, very, very expensive. So you can't be, you don't have the luxury to boil it up to more than 2000 degrees Celsius. So what you would do then, you would add to it what we call cryolite. Okay, so what does cryolite do? Cryolite. So cryolite, it also has aluminium within it. What it does, it dissociates aluminium oxide. It dissolves it, because like I said, we want aluminium oxide into its ions, okay? Al3 plus and oxygen O2 minus. We want it in its ionic form. So cryolite helps to dissolve this aluminium oxide, and as it dissolves it, okay, the boiling point, remember, like I said, the boiling point, sorry, the melting point, not boiling point. Have I been saying boiling? I'm sorry, you're trying to melt it here from solid to liquid. Okay, molten. Okay, so the melting point is very high. Like I said, it's more than 2000 degrees Celsius. But the melting point of cryolite is actually, it's not that low, but it's lower than the melting point of aluminium oxide. And that's why we use that cryolite, because it dissolves aluminium oxide. And once it dissolves it, you would have then as your electrolyte, or within your electrolyte, you would then have your aluminium 3 plus, okay, aluminium 3 plus, and you also have your oxygen 2 minus oxide, okay, and then there are also other stuff that you get from cryolite. You can go and Google what cryolite consists of, or I'll write it down at a later stage. But yes, so you basically now have aluminium oxide in its ionic form, which is what you want. Okay, and here's another thing in this sketch that I wanted to show you. Your anode and your cathode are actually made of carbon, specifically graphite. Okay, so you have graphite there at the anode, okay, and so I'm just going to put carbon there, which stands for the graphite, and at the anode, so you have a steel covering. So this blue part out there, that's like your steel protection, if I could say, your covering. Then you have lined on the steel covering is also graphite, and that is basically your cathode. Okay, hence I put the negative charges there. So basically what would happen, because you want aluminium, remember your cathode is negatively charged, so your aluminium will go all the way to your cathode, right? It will go to the cathode, and basically it will be reduced, all right, to the aluminium here. So you'll have aluminium, okay. In your table of standard reduction potential, I think it puts it as a solid, but here, because it's actually quite molten, I would rather say it's a liquid, honestly. Okay, because it's in a molten form, because it comes out here, it exits here as aluminium, okay. And I'm gonna put it as a liquid, but ultimately it will solidify. All right, so that is the process that we go through to extract aluminium. Like I said, it's very, very expensive. So the use of cryolite helps to reduce the costs. Okay, so this is what happens at the cathode, okay, where reduction occurs. I'm going to put space there for oxidation, because we normally start, whenever you have to put the net equation, you start with oxidation, and then you have reduction, and then at the end you put your net equation, but we'll get to an example. So with reduction, we said you have your aluminium ions, okay, thanks to cryolite we could get the ions, and then they reduce there at the cathode, which is your graphite. Okay, so let's go look for aluminium. I'm going to start from the top. Oh, there is aluminium. Hope you see it. 3 plus. Obviously, you're going to have 3 electrons. So, yeah. And this aluminium here, it's both aluminium from aluminium oxide as well as cryolite. Let me actually go and see if I can get the equation for cryolite for you guys. Okay, where is cryolite? Okay, so cryolite is made of sodium, aluminium, as well as fluorine. Okay, so that's pretty much, so this aluminium here from cryolite, it will also be reduced. Okay, so we saw the reduction, the half reaction that happens at the cathode. You have your aluminium 3 plus, because the charge is 3 plus, you'll have 3 electrons. Okay, and then like I said, with aluminium, with reduction, you write it as you see it on the table. So then at the end you're gonna have your aluminium, which will ultimately become a solid. Let me see, did they actually put, no, they didn't put it. Okay, I thought they put a S there as a solid, but yes, it will ultimately become a solid. Okay, and then at the what is oxidized exactly? So what is oxidized? You have your oxygen, right? Your oxide ions, and they will be oxidized, right, at the anode. Okay, so your oxygen ions, they go there to be oxidized, okay, at the anode. And what happens then? If they get oxidized, then you end up having oxygen gas. Okay, so yeah, so that's oxygen that's produced. Actually, let me put it this way. No. Okay, so you have oxygen that is produced. Okay, but remember you have oxygen there, and your anodes are made of carbon in the form of graphite. Okay, so what actually happens there is, now you have another reaction. You're gonna have oxygen that sees the carbon there. Okay, that's a gas. And then at the end, you're going to get carbon dioxide gas. Okay, so what actually comes out there, the bubbles that come out, that's actually going to be carbon dioxide gas, not oxygen. So carbon dioxide gas. The oxygen gas will actually surround the carbon. Okay, and because it's surrounding the carbon, it's eating away at it to form carbon dioxide, and therefore, as always, the anode loses mass. Okay, and at the cathode, you gain mass, obviously, when aluminium is busy being formed. Okay, so yes, now let us see the half reaction for what happens at the anode. Okay, so while we go to that table, I want to mention something else. Because now you're going to form carbon dioxide gas when oxygen reacts with the carbon, these anodes need to be replaced often. Okay, and if they will be replaced often, it means that again it contributes to the cost of the extraction of aluminium, because you continuously have to replace anodes because they're being eaten away by the oxygen. So another reason why this process is quite expensive. Okay, so let's go see where we can get oxygen. It being oxidized, sorry, the oxide ion being oxidized to oxygen. Okay, let us see, are we gonna get anything? Okay, so we can't really use this one because it forms water at the end. We don't want water, we want, how? No, I missed it. Okay, I missed it somewhere. No, it can't also be this one because we don't want to form H2O2. There really is nothing for oxygen. There has to be. Okay, I'm not seeing anything unless if no, guys. We're supposed to get the oxide ions, and I'm not seeing them here. What is going on? Okay, I'm really not seeing oxygen here in its ion form, which is weird. But basically, the equation is supposed to look like this, guys. I will investigate further. Okay, so we have oxygen ions. Maybe you will see it. I don't know. Oh, I keep forgetting to put this. So oxygen ions, okay, and then it would give away its 2 electrons to form oxygen gas. Okay, so did I even write that correctly? Let's see. Because I have two there. Actually, I'm gonna balance it with 2, but now I have 2 over there. I'm gonna need 4 electrons. Am I doing this correctly? Yes, because no. Let's see, guys. So we have O2 here, ne? So it means we're gonna need 2 oxygens there, and then the charge here, we're gonna need actually 4 electrons over here. Okay, but where is this in the periodic, in that table? Okay, I can't find it. Really, I cannot. So yeah, but basically we are done with these, and now we're gonna look at a question paper. Okay. Yeah, so as we look for a question paper, another thing about this extraction of aluminium bauxite before I close it off is, why do we actually need to extract aluminium? It's actually one of the most abundant minerals on the earth, and we use it for so many things. The nice thing about it is that it doesn't corrode. So for that, it's going to be used a lot. Your cold drink cans, they're actually made from aluminium. It's actually quite ductile, and can be formed into like very thin sheets. So hence, you can use it to make your cans for cold drink or beer or whatever. And also we use it in airplanes. So the metal that is used to make airplanes is aluminium, because also apart from it being light, malleable, ductile, it's also low in density. And I mean, if you're gonna have something in the air, you don't want something that's very heavy. So it's used for that. What else? You use it in power lines. So aluminium would be used if you look at the power lines, or yeah, you'll see it there. But you can go read about more of its uses. But at the end, because we are producing carbon dioxide here, I did mention it's quite expensive. It's an expensive process. But because we are also producing carbon dioxide, it does, affect the ozone layer and global warming and all of that. So yeah, so most people would rather recycle aluminium instead of extract it from bauxite because the whole process is expensive. They've tried with cryolite to actually reduce costs, but it works out better to recycle aluminium than to extract it. Yeah, so let me get a question paper. Okay, and let us see how we can apply all this knowledge. Okay, so I'm looking at a 2015 paper, and this is for the electrolytic cell. Okay, so what I'm gonna do, I will separate the two such that they can be side by side and we can answer questions and end. Okay. And then after this, guys, we are done. This is 12 marks. This should go by quite quickly, I think. All right, so it says the simplified diagram below represents an electrochemical cell used for the purification of copper. We've discussed this, so yeah. Now they say define the term electrolysis or electrolysis. Okay, so we said that electrolysis is the process. It is a chemical process, first of all. My pen has started again. Okay, it is a chemical process, number one. Okay, where electrical energy is actually converted, or electrical energy produces chemical energy. Okay, so that's that for 2 marks. And then 9.2, give a reason why a direct current source is used in this experiment. Okay, because we require electrical energy, guys, you're gonna have to need a source and a DC current. Remember, direct current is stable. Oof. And let's try this. It's actually more stable than alternating current. Okay, so it would do something like this. Okay, let me try again. So if you have a voltage or whatever, okay, this is not working out when technology fails. Okay, so we have, if you have a DC source, now you have consistent. I just wanted to put this. So you have a voltage that's pretty much consistent. Okay, but if you had an alternating current source, so AC, remember alternating, it is alternating in nature. Okay, so it would do something like that. So if you want to check out what the voltage is at a certain time, it varies. Okay, it changes with time, so it's very unstable to use an AC source. So a direct current source is perfect because it's stable. Okay, and then 9.3. Yeah, I'm actually struggling to write. Okay, 9.3. Write down the half reaction which takes place at electrode A. First of all, let's talk. What is electrode A and what is electrode B? Okay, if you can remember, we did say that where you have impure copper, that is the anode. If you forget what happens at the anode, think about it losing mass. So wherever you are losing mass, that is the anode, because that is where oxidation occurs. Wherever you are gaining mass, that is the cathode, because reduction occurs there. You are gaining electrons. Okay, so electrode B is the anode. So now what would happen then at the electrode A, that would be reduction. That is the cathode. Okay, so if we're going to write down the half reaction, what takes place at electrode A, when we use our table of standard reduction potentials, we're not going to change anything. We're going to write it as is. And then copper. Okay, which copper? There's this copper plus 1 electron, and then we have copper 2 plus with 2 electrons, and then you have copper 2 plus with 1 electron. So which one do we use? We're going to use copper 2 plus, okay? And we're going to use copper 2 plus, which gives us a copper 1 plus ion, or are we going to take copper 2 plus, which gives us the copper solid? We want copper solid. We're busy purifying it, so the one that gives us the solid is the one we take. Why aren't we using copper 1 with 1 electron there? Well, basically that one, we don't use it because the electrolyte that you use, remember, we're using copper sulfate. Yes, and that copper in that sulfate has a charge of 2 plus. Okay, so the half reaction that takes place at the cathode, okay, will be copper 2 plus. Okay, and then we're going to add 2 electrons, and then we have copper, the solid, which is what we want. All right, let's go back to the question. And guys, please go over our videos where we actually go through question papers, past question papers. We've done quite a lot. If you can't understand this topic, really go over those past papers. And while you're at it, please like and subscribe. Like our video, subscribe to our channel, share this information. It's quite valuable. All right, so 9.3, write down the half reaction that takes place at electrode A, which is the cathode. We've written it down. 9.4, so it says, due to small amounts of zinc impurities in the impure copper, the electrolyte becomes contaminated with zinc 2 ions. Remember, this is impure copper, guys. There are other metals in it. Okay, I did say, I think as we were doing the theory, that you sometimes get like silver, you get gold, you get platinum, you get impurities that settle at the bottom. But within this electrolyte, now they're telling us there are zinc 2 ions present. Okay, so what do you have now? You have zinc 2 plus and you have copper 2 plus, and you want to know which one will win, which one will actually go and attach itself to the cathode. Is it going to be zinc? Is it going to be copper? And you're going to use your table of standard reduction potentials to actually figure that out. But let's see. So it says, refer to the attached table of standard reduction potentials to explain why zinc 2 ions will not influence the purity of the copper obtained during this process. Okay, we can be confident that it will not affect its purity. Why? Remember, on the left-hand side, you have increasing oxidizing ability. That's like saying the oxidizing agent increases as you go up. Okay, the oxidizing agent, that's a substance. What is the process? The process is reduction. So as you go up, you want to know which one will be reduced first, or will be most likely reduced. Will it be zinc or will it be copper? So one that is on top, so if we have zinc and copper, the one that is above the other will be the winner. Okay, so we know that copper is somewhere around, where is copper? We were talking about it now. Okay, so this is the copper 2 plus, right, which has a voltage of 0.34. Where is zinc? I get it. We want to know, why is it purely copper and not zinc? We are expecting zinc to be below copper. If zinc is above copper, guys, we are in trouble. That copper will not be pure. It will contain zinc as well. So we have copper here, which is 0.34. Now let's look at the bottom. Let's not even bother going to the top. If we look at the bottom, there is zinc. Yes, zinc was supposed to be there, or else you wouldn't get pure copper. So we see that actually zinc, it has an E of, or EMF of negative 0.76. Okay, and copper has an E of, or EMF of, I forgot what we said, 0.34. Okay, so yes, zinc is quite low. Okay, it does not stand a chance to be reduced more than copper. I mean, it's in the negatives. If maybe it was 0.33, maybe you might find some traces of zinc inside that purified copper, but it is so low that we're not expecting it to even become part of the purified copper. So that is what I would say. You look at your table, you compare the positions of it, okay, and by so doing you say that this one, copper, okay, the chances of being it has a high I don't want to say reducing ability, yeah, but it would reduce way more than zinc would, okay, so it has a high reduction. It will reduce way more than zinc would, okay, and it's 3 marks, so I guess you have to probably write down there the voltage, okay, and say that it is likely to be reduced, like proper, more than it would zinc, okay. And then it says, after the purification of the impure copper was completed, it was found that so many moles of copper were formed, okay. So the number of moles that we have there, 9,5, so 9,9, number of moles, it's going to be 2,85 times 10 to the power minus 2 moles of copper. Okay, this is the pure copper now. And it says the initial mass of electrode B, meaning the impure copper. Okay, so the impure copper is actually 2 grams. Okay, calculate the percentage of copper that was initially present in electrode B. Okay, so calculate the percentage of copper that was initially present in electrode B. Okay, so we're expecting that copper to actually be less than 2 grams, okay, because it's the impure one. So I would then start by getting the mass of this copper that they give us, okay. So the mass, if we want to get mass, remember the number of moles is equal to the mass over the molar mass, okay. So the mass is number of mole times molar mass. And copper, if we have a look at the periodic table, copper is actually 63,5. So first of all, the number of mole, we have 2,85 times 10 to the negative 2 mole. And we're going to multiply by 63,5 grams per mole. So our answer will be in grams. Okay, so let us get the calculator and we bring it out shortly. Okay, so we have the calculator. So 2,85 times 10 to the power minus 2 times 63,5. So we have 1,8. Yeah, we were expecting it to be really less than 2. So we have 1,8. 1,81. Let's just say 1,81. And then what was the actual question? I feel like I forgot what they were actually asking. So that says calculate the percentage of copper that was initially present. So you would have to use, I would say, percent purity. I don't know if you remember that formula, but the percent purity obviously will be the pure copper over the impure copper, and we multiply that by 100 because we want a percentage. So the pure one was 1,81 and the impure was 2, and if we take that and we multiply by 100, is the calculator, so we have that value, this value, okay, and we divide it by 2 and we multiply it by 100. So actually the percent purity there is 90,49%. Okay, or you could say 90,5. Like it's pretty close. 90.5%. Okay, yeah, that's the percent purity. And guys, we are done with this session. I really hope you enjoyed learning about electrolytic cells. I'll see you next time for galvanic cells.